All right, good morning, everybody. Well, it's morning for me at least. Welcome back to another week. This week, we talked about free fall acceleration and other types of parts of motion. Um, we're getting into talking about the reason that things move, the reason why things move, which will be we're getting into that next week. So we did discuss in those videos a little bit about forces, but we'll talk more about that next week. Today, I want to show you guys how to do some simple motion problems, right? We're just going to work a few examples like you would see if you were to do some of the math in the problems that we were working. So basically, I'm going to go through these slides, show you a few examples. We're going to talk about them. We'll talk about a few of the concepts as we go along. If there's anything in the videos from before or from today that give you any trouble, please just reach out to me and let me know. So as we talked about this week in the other videos, all objects, when they fall due to gravity, at least on the surface of the Earth, right, they all fall at the same rate. They're all going to accelerate at the same rate. And that rate of acceleration due to gravity, 9.8 meters per second squared. It means for every second, it's going to speed up by 9.8 meters per second. So about 10 meters per second every second. That's a good way of estimating, but I'm going to show you how to actually directly calculate these things. Because when something is in free fall, when any object is in free fall, that acceleration is constant, we can use equations to solve for distance, time, and initial and final velocity. And I showed you one of these equations last week, but these are called kinematic equations. And there are three of them. They look something like this. Recognize my notation here. Delta t and delta x, those represent changes in time and changes in position. So delta x is really x final minus x initial. Right? Same thing with time. But we don't really have to write it that way because of the way that we will talk about the problems. Okay? And so that's why you see the deltas here. Those are just single variables. Okay? A represents the acceleration for whatever object we're talking about, initial and final velocities. Okay? And then I think those are the only ones we got there. Yeah. Now, recall that the direction of motion matters. Okay? We are talking about vectors here. Right? So if the acceleration and the velocity are in the same direction, the object's going to speed up. But if they're in opposite directions, it's going to slow down. And so the direction matters. So we're going to talk about how to incorporate the direction into what you're doing in these problems. And just one thing before we begin on any of the examples, pretty much everything that we're going to do just completely ignores air resistance. And though we will do some experiments this week where you'll get to see how air resistance can play a role in what's happening, mathematically, it makes it really, really complicated. And so there are a few reasons that we're just going to ignore air resistance when we're calculating things. Now, the first one is when you're dealing with smaller objects, similar objects with small velocities, so they're not going really, really, really fast. Right? Air resistance is generally not really going to play a role in the calculation anyway. Okay? It takes a couple of seconds for, if you drop two coins, they're pretty much going to hit the ground at the same time, regardless of how air impacts them. Okay? The air is not going to impact two coins like a penny and a quarter differently, so much that if you drop them at the same time, they won't hit the ground at the same time. In your demonstration this week, if you use the textbook and the piece of paper, well, those two things are different enough that you can see the effect of air resistance. Okay, but if we're talking about things that are similar enough where you can't really see the effect of air resistance, then we don't have to think about it so much when we're trying to answer some of these questions. The other reason is that air resistance varies based on your speed. And you can test this by sticking your hand out the window when you're driving down the road. Don't do this in any kind of dangerous way. If you're going about 10 miles per hour, the wind will blow in your hand. If you're going about 60 or 70 miles per hour, it'll blow your hand backwards, and it's kind of hard to get it to move forward, right? And so this is why, or just a good way of demonstrating that air resistance varies based on how fast you're going. Okay? So that anything that varies like that is going to require calculus to figure it out, and we're not going to deal with that. Nothing like that in this class whatsoever. But there's a lot we can still learn and talk about, even if we just pretend like air resistance isn't there. Okay, it is, and in real life you have to think about it. Okay? But for our purposes, we can still discuss how objects move without discussing air resistance. So let's discuss for just a moment how objects move. Remember that in all of these examples, we're going to have a constant acceleration. That's going to be important. So a car's traveling at 45 meters per second, and it hits the brakes and comes to a stop in 5.8 seconds. What's the acceleration of the car after the brakes are applied? Well, the thing here we need to do is, for all of these problems, you're going to want to use those kinematic equations, those three equations. You just have to figure out which one's the easiest one to use. And so here we have a car traveling at 45 meters per second hits the brakes, right? So the initial velocity, 45 meters per second. It hits the brakes and comes to a stop. Well, if it comes to a stop, the final velocity is 0. Okay? And then it does this in 5.8 seconds. So our time, 5.8 seconds. To find the acceleration, we can use the equation Vf equals Vi plus A times delta t. Our Vf value is 0. Vi is 45. Plus A, which is the thing we're looking for, acceleration, and times 5.8. So now, to find A, you have to solve for this algebraically, right? So subtract 45 from both sides. We can just 0 minus 45, I'm just going to go over here, is negative 45. Equals 5.8 times A, and then we just divide by 5.8. You guys, if you have trouble with these algebra issues, just let me know. I'll be happy to share some algebra videos with you that can help with these solving these types of problems. Negative 45 divided by 5.8 will give us an acceleration of negative 7.7676 meters per second squared. Notice that the acceleration is negative, right? It's slowing down. It's coming to a stop. That's going to be important when you're considering the acceleration in later problems, okay, when you're talking about what the value is, and when we're talking about directions of objects moving. So now we have the acceleration of this car. How far does it travel before it comes to a stop? Now, this is a slightly different equation from the list, okay, but we can use the one where we have delta x, which is our distance or our displacement, how far the car travels. That's going to be equal to the initial velocity times delta t plus 1/2 times A times delta t squared. The initial velocity was 45. Oh, 45, not 4.5. Time was 5.8 plus 1/2 times negative 7.76 times 5.8 squared. This gives you delta x is equal to 261 plus negative 130.5. I did a little bit of rounding here, you guys. And so that means delta x, the distance that the car travels, is 130.5 meters. So that's how long it takes, or that's the distance that it travels before the car stops. So long as we're working on the same problem, all these values are pretty much going to kind of stay the same. We are going to break some things up in just a few minutes. But now let's talk about cars travel horizontally, right? And they only accelerate because you hit the accelerator or you hit the brakes. Okay, but what about if we drop something, right? Something in free fall. Right? Remember velocity and acceleration are vectors, right? Displacement is a vector. And so the direction that these objects move is important. Okay, so when we're dealing with free fall acceleration, right? If you drop something, it falls straight to the ground. If you throw something up in the air, it'll go up for a minute and then turn around and go straight to the ground. Okay, and so we have to talk about the different directions. Generally, when we do these types of problems, we consider up to be positive, okay, and down to be negative. And so as an object falls to the ground, it'll just speed up by about 10 meters per second every second. Okay, the acceleration due to gravity is 9.8 meters per second squared. But if it's always pointing downward, we have to keep that sign in there when we talk about it. And so whenever you're dealing with free fall acceleration, if you're going to use up to be the positive direction, then A is going to be negative 9.8 meters per second squared. In the same way, if an object falls downwards, if the distance that it travels is downwards, then delta x will be negative. Okay, the final minus the initial position will be negative. The change in position. And you should see that here in an example in a few minutes. We'll have to use that. Actually, it's this example, I think. So I told you guys, I believe, the story about Galileo and the Leaning Tower of Pisa. Let's say Galileo releases a ball from rest at the top of the Leaning Tower, which is 60 meters tall. How long does it take for the ball to reach the ground, right? So how much time does it take before it hits the ground? Okay, well, we're dropping it from rest, so we know that our initial velocity is 0. Okay, we know the distance that it travels because it's the height of the building, which is 60 meters. Okay, but again, this is what I was saying just a second ago. If it's 60 meters downwards, then delta x is going to be negative 60. If you make a mistake here, right, you'll see that your answers kind of won't really make much sense. Oh, I'm sorry, guys. My kid is also home sick today, so you might hear him in the background every once in a while. And then finally, our acceleration, negative 9.8 meters per second squared. And so we can use delta x equals vi delta t plus 1/2 a delta t squared to find the time, to find delta t. Okay, with no initial velocity, this component just goes to 0. And so delta x is negative 60 is equal to 1/2 times negative 9.8 times, I'm just going to write it as t squared. This will give you, and I'm just a little out of space here, negative 60 divided by negative 4.9. And that will be equal to t squared. And so that is 12.24. You would then take the square root of both sides, and you'll find that t equals 3.5 seconds, 3.50 seconds. And so that's the time that it takes for the ball to reach the ground. It takes about 3.5 seconds for something to fall 60 meters, if we ignore air resistance. So that's pretty quick for it to be that high up in the air. But this is accurate, as you'll see in a few weeks when you do some of these types of experiments or do a little more with this. Okay, so now that we have the time that it takes for the ball to reach the ground, what's the velocity and the speed just before it hits the ground? All right, so what's the final velocity? And well, we know the final velocity is equal to the initial velocity plus a times delta t. We just found the time, right? The time was 3.5 seconds. The initial velocity, he just dropped it. He didn't throw it downwards or anything like that. So the initial velocity is 0. Starts from rest. And our acceleration, again, negative 9.8 meters per second squared, okay, because it's pointing downwards. Notice things like time won't have a negative sign because time cannot go backwards in any of these cases. Now, to find the final velocity is equal to 0 plus negative 9.8 times 3.5. And so this thing is traveling at about negative 34.3 meters per second. Right? So this is our velocity. Negative 34.3 meters per second implies that it's 34.3 meters per second downward, right, as it's falling. The speed does not include the direction, so the speed is just 34.3 meters per second. This is how fast it's going. This is how fast it's going and in which direction it's traveling. Okay, that's the difference between the two answers. Okay. You guys, I'm gonna break this video up for just a second so I can see what my kid needs, and I'll be right